You know, the kids will come in, oh my gosh, it smells terrible in my room. Well, after a short amount of time, they don't even notice that it smells in here anymore because those nerves become used to that. So receptors are typically associated with skin, muscles, joints, and other viscera, eyes, things like that, make up your general somatic senses. So here we're looking at touch and pressure. Free nerve endings are what's going to be in the epithelial tissues. So the end of my nerve, the free nerve ending, is what's going to be present in these areas. Tactile are Meissner's corpuscles. Our flat connective tissue sheaths surround 2 or more nerve fibers. They are abundant in hairless areas and very sensitive to light touch. Your fingertips would be an example of an area that has a lot of Meissner's corpuscles. Very sensitive to light touch. Lamellated or Pacinian corpuscles are large structures of connective tissue. They look like an onion, and they function to detect deeper pressure. So Meissner's corpuscles, light touch. Pacinian corpuscles, deep pressure, is the difference between those two. And if I look at these, so here's the Pacinian, and it looks like layers of an onion. And if you look under a microscope, it's usually stained. It looks just like a red onion. You can see these layers that are around it. A tactile or Meissner corpuscle looks more to me almost like your digestive system. It looks like intestines that are wrapped around in different areas. And what happens is these nerves are located in different places. So your free nerve endings and your tactile corpuscles are going to be located close to the top of your skin. Light touch. They're going to notice little light touch. If I take a toothpick and barely touch you, this is what's going to pick it up. Your Pacinian or lamellated corpuscles are found deeper in your skin, therefore they're going to pick up pressure that's deeper and felt further down. Temperature, like I said, they have 2 groups. You actually have warm receptors and cold receptors. I have done a lab where if you take a cold metal, I can use anything that's a cold metal, and touch in certain areas, you'll notice that certain areas of your body pick up cold better and certain will pick up hot better. Both heat and cold receptors adapt quickly. You notice this when you take a shower or a bath. I know a lot of people find it gross, but I love a hot bath. And when you get into the tub and it feels very hot, and you sit in there for about 3 or 4 minutes and you're adding more hot water. Do you notice that? Or even in a hot shower, it feels hot right away, but then your body adapts very quickly. So that's why you get into the hot bath, and after a few minutes you can add more hot water because your warm receptors are going to adapt to that very quickly. However, when it gets too hot or too cold, you're going to actually have pain, and I'm sure you've noticed that. If I put the shower on too hot, it hurts. I can't even get in. So temperatures near 45 degrees Celsius stimulate pain receptors, and then temperatures below 10 degrees can also stimulate pain. And same thing, when you're outside and your hands get so cold that they hurt, it is now your pain receptors that are picking that up. So your pain receptors themselves consist of those free nerve endings that are up towards the top. They're stimulated when tissue is damaged, you cut yourself, and they do not adapt as much. So your temperature, your thermoreceptors adapt very quickly, your pain receptors do not. And here, like I said, they're found in your body except the nervous tissue of your brain. Your brain has no pain receptors. Many stimuli can affect your pain receptors. We just talked about temperature can cause pain. Also chemicals, even like a strong chemical smell can burn your nose and cause pain. So chemicals can cause pain. Oxygen deprivation, which hopefully you'll never experience, but that can also form pain. How pain receptors are stimulated is still not completely understood by the scientific world of, how is pain actually felt. Visceral pain receptors are actually found obviously in your viscera, so like in your abdominal area and things like that. Pain in this area seems to come from some type of pressure, mechanoreceptors. Could be caused by a decreased blood flow, chemicals, they're again like heartburn and things like that. Spicy foods might cause a pain or a pressure in a certain area in your digestive system. Referred pain also happens in your organs. So when visceral or organ pain is felt in another body area, this usually happens because the nerve that picks that up can go from the skin to your internal organs. So some of your nerve cells are very, very long, so it might pass from one area to another. Some common ones would be, probably the most common one would be like a heart attack. When someone has a heart attack or is at the beginning of a heart attack, a lot of times they talk about numbness or pain in your arm. That would be a referred pain. So, yep, your chest might hurt, but you're also going to feel something in your arm. And then you can look at this. There's some other, for example, liver, gallbladder, yep, they're found here. This makes sense. But sometimes you also have issues in the neck region that come from your liver. That would be a referred pain. Appendix, that pain is a sharp abdominal pain, and it's pretty close to where your appendix actually is. This just shows a system of a nerve. So this nerve comes along this pathway. Here I have skin, and they end up coming together, and that's kind of how you can get your referred pain. Fibers that conduct pain away are they're classified as acute pain or chronic pain. Acute and chronic are terms that you're going to hear a lot if you go into the medical profession. Acute pain fibers, they're myelinated, so they have a sheath, they have a covering over it, and they carry impulses very quickly. Acute pain would be a sharp pain, might be short-lived, it comes on all of a sudden, and then maybe it'll go away for a while, and then it'll come back. So acute pain is a sharp, short pain. Chronic pain, so anything that you have that's chronic fibers don't have that protective, they don't have that myelin sheath on the outside. They conduct impulses slowly, and that's going to end up to a dull ache instead of a sharp pain. So a dull ache that may last for a long period of time. Pain impulses are processed in the gray matter of the dorsal horn. So looking at the spinal cord, if you look back a couple pictures where they had a picture of the spinal cord, there's gray matter and there's white matter. Pain is typically processed in the gray area. And then they're going to go to the thalamus, the hypothalamus, and the cerebral cortex. They're going to go to the brain to be processed. So a person becomes aware of pain when that impulse reaches the thalamus of the brain. But the cerebrum, or the cerebral cortex, judges the intensity and the location and whether it hurts enough that you're going to cry about it or not. So thalamus picks up the impulse first, but your cerebral cortex is what processes how bad it is. So if you've been to the doctor for something and they always have the little pain chart, on a scale of 1 to 10, how bad is your pain? The cerebral cortex is the part of your brain that's telling you, oh my gosh, this is a 10, it's killing me, or it's about a 2, it doesn't really hurt all that bad. And that cerebral cortex, which when you think about it, you know, why do we cry when we get hurt? Your tear ducts really have nothing to do with muscles, so it is your cerebral cortex that deals with that emotional part also of, you know, oh my gosh, this hurts so bad that I'm crying. Gray matter, like I said, regulates the flow. That's where it's going to go first. And then it can trigger the release of a couple of hormones, enkephalins and serotonins. Both of these are going to inhibit the release of pain impulses. So a lot of times when people get hurt, you know, they cut themselves, severe damage, and people might go into shock for a short period of time. There are chemicals in your body that actually help to slow down, inhibit that pain so that you don't feel it so intensely. And endorphins are a chemical released in the brain that provide natural pain control. And endorphins are released like when you exercise. They're kind of it's a feel-good chemical. And there are things that you do that actually increase the release of endorphins, exercise being one of them. They talk about how exercise is very important for like your mood, and I know I like to run or jog or whatever, and when I'm done running I feel good, and those endorphins are produced. Excitement and things like that can also release endorphins. These natural painkillers are actually considered, they'd be in the family of an opiate, which is like morphine. So when you're given artificial morphine or the chemical morphine at the hospital, your body actually produces something very similar to morphine on its own to help prevent some of that pain. And that's where we'll stop.